Chemicals. For the average person, storing them might not require much thought. Daily chemicals such as rubbing alcohol, acetone, vinegar, or acetic acid can all be stored in one compartment, on different containers of course. And in the case that they do accidentally mix with each other, all you get is a mess you can clean up in minutes. Now, what if a company or an organization needs to store these chemicals, bromine, chlorine, ammonia, copper, and iodine? They can store it in one warehouse. But should they?
For example, mixing iodine and ammonia can form nitrogen triodide. Yes, it's a fancy chemical name, but the results, well, not so much. That's because the reaction of mixing these two chemicals can cause explosions and other hazards in the process. And this is the issue. Certain chemicals are incompatible with each other. So storing them together in one compartment is not the best idea. This table shows the list of chemicals mentioned earlier and their incompatibilities. So, how do we store these chemicals?
The simplest way is to store them in X number of compartments, given that there are X number of chemicals. So, for our problem, 5 compartments can be used for the 5 chemicals. We store bromine in compartment 1, chlorine in compartment 2, and so on until all are stored. This does prevent the issue of hazards, but it brings a new problem to the table: cost.
While incompatible chemicals need to be stored separately, compatible chemicals can be stored together to minimize cost.
This is where graph theory and the concept of vertex coloring come into play.
In simple terms, a graph in graph theory is like a collection of dots called vertices or nodes connected by lines called edges. And vertex coloring is the process of coloring each vertex such that vertices connected by an edge do not have the same color.
We represent a chemical storage problem by representing a chemical as a vertex and adding an edge between them if they are incompatible with one another. This means that a color will represent a warehouse, and those chemicals assigned with the same color will be stored in the same warehouse. Hence, minimizing the number of colors means minimizing the number of compartments.
Thus, this is how our problem earlier will look like, from a table to a graph. Then we can use vertex coloring to segregate these chemicals. This can be done by using an algorithm that can also minimize the number of colors. In our case, we will use the Welsh-Powell algorithm.
The Welsh-Powell algorithm is as follows. Oh no, that's a lot of information. How about we simplify this? There, much better. Let's apply this to our problem. First, we list the number of connections of each vertex and order them in descending order. Then, since ammonia has the most number of connections, we assign the color blue to the chemical. Then, we move down into the list and assign the color blue to the ones not connected to ammonia. So copper will also be colored blue.
We now repeat the process since no more chemicals can be colored blue. Going through the list from the top, we pick bromine. Bromine is indeed tied with chlorine, but in case of ties, we can just pick randomly. Bromine is now assigned a new color. Let's just say red. Then continuing, iodine is also assigned with the color red. Repeating the process again is easy, since chlorine is the only one left uncolored. We can just pick color green.
Now, finally, since each color represents a warehouse, Warehouse 1 will store ammonia and copper, Warehouse 2 will store bromine and iodine, and Warehouse 3 will store chlorine.
Yay! We now segregated the chemicals properly and also minimized the number of compartments. Imagine if we store them in 5 different compartments instead of just 3, that would be expensive.
And with this, we were able to apply the concept of vertex coloring in graph theory to solve a real-life problem of chemical storage. This video is based on our exposition paper using vertex coloring algorithms to solve storage problems of chemicals. This paper is our final course output for the subject of graph theory and its applications in the second semester of school year 2023 to 2024 in Bulacan State University.
You can read more about our paper in academia.edu under the account posted by Yvan Lowell P. Aquino, where we actually discuss other coloring algorithms beside the Welsh-Powell algorithm. And with that, I'm Yvan Lowell P. Aquino, the scriptwriter of this video.
Liah Francheska, si Baculi, one of the main presenters.
Justine, Magedi, and Santillan, also one of the main presenters.
My name is Ramil, Angelo, and Rosal, the main editor for this video. And with that, thank you for watching.